Hi folks, got a relatively short video lecture for you today. This time we're going to be talking about some other modeling frameworks that we don't really get into very much during this class, but you can get into in classes like IEE477 and some other classes offered elsewhere in the university. But I at least want to give you some exposure to them in this one. But before we get to that, let's talk about Lab 3 that's coming up. So in Lab 3, we introduced Monte Carlo simulations last time, and you'll get a chance to practice those during Lab 3. Just as a review, a Monte Carlo simulation is a type of simulation where we run a single run of a sim, and then we take the output of that sim, we call it a sample, and then we gain insight from running potentially very many, thousands even, of those simulation runs, and then all of those samples, like experimental samples, we might take a distribution or an average and so on and so forth, and that's where we end up getting our inference from running the simulation multiple times. In Lab 3, you will use this method actually to estimate pi. Now that might seem a little strange, but the basic idea, this is a slight modification of what you'll do during Lab 3, is imagine if you had an area of wall that was a wall which had a certain height h and width w, and you hung a dartboard, so a circle in the middle of the wall somewhere that had a radius r. Now the area of that dartboard is pi r squared, and if you could manage to throw a dart uniformly anywhere on that wall, so you weren't actually aiming for the dartboard, you just randomly threw the dart, and if you could guarantee that it would sort of land in a uniform horizontal and a uniform vertical position on the wall, then it turns out that the probability of you hitting that dartboard would be just the area of the dartboard divided by the area of the wall. So pi r squared divided by hw. So because the area of a dartboard has a pi in it, then we can actually use the Monte Carlo sampling to estimate the probability of hitting the dartboard, and then equivalently estimate pi, because we can end up rescaling that probability that we estimate from the experiments by hw and r squared, end up getting pi out. And so that's sort of what we're saying here. You have the area of the dartboard divided by the area of the wall. That's pi r squared divided by hw. This should be approximately what proportion of throws hit the dartboard. So if you throw a bunch of these throws and then estimate that proportion, you might find that, say, 50% of your throws hit the dartboard, or 20% of your throws hit the dartboard, or whatever. Well, if you solve this expression for pi, then you find out that the number of dartboard hits divided by the number of total throws scaled, so this is the sort of proportion that of your throws, proportion of total throws that actually hit the dartboard, scaled by hw divided by r squared, gives you an estimate of pi. So in, say, Microsoft Excel, you can actually draw a random x-coordinate, and that x-coordinate you can draw just as uniformly distributed between 0 and 1, and a random y-coordinate that's also uniformly distributed between 0 and 1, and that's like your dart hitting a particular horizontal and vertical position. And then you just check to see, did the dart hit the dartboard? And if it fell within the dartboard, you count that in the hits column, and if it didn't, you count it in the misses column, and then you count how many hits divided by total throws. That gives you your proportion, rescale, and you get pi out. You do that 10,000 times or so, and you actually have a good estimate of pi. So strangely enough, drawing random numbers can allow you to estimate something like pi. So that's kind of interesting. So you'll try a method of doing that during the lab, and you may also actually hear about another way to estimate pi by drawing random numbers in the lab intro. So you might think about, how could you possibly do this in a similar method if you wanted to simulate, say, an unfair coin that has an 80% probability of landing heads up. So if you think about that for a second, you should be able to do something similar here, but you don't really care about pi being involved. So imagine you take that wall and you paint it so that 80% of the wall is black. If you throw that same dart, then 80% of the time you're going to hit a black spot, and 20% of the time you're going to hit a white spot. So if you throw that dart, then if it hits a black, you can call that a heads, and if it hits a white, you can call that a tails. And then if you throw that dart 10,000 times, then 80% of those 10,000 times will end up getting roughly 80% will end up getting that heads. And so you've managed to implement an unfair coin toss using darts and a black and white wall. Now, of course, it's a little silly to use both dimensions there, so it's just easier just to paint a single line, so just the horizontal dimension, and paint 80% of it black, and then leave the other 20% white. And then instead of throwing a dart in two-dimensional space, you can throw it just along that one-dimensional space, and that's effectively what we do when we need to draw a single random number that comes up 80% 1 and 20% 0, as we just draw a random number between 0 and 1, and then we ask if that random number is less than 0.8. If it's less than 0.8, then we call it a 1, and then that 1 will happen 80% of the time, because a random number drawn between 0 and 1 will be less than 0.8 80% of the time. All right, so we'll see more of that as we go on. But this general idea is called rejection sampling, or the acceptance rejection method. So it's this idea that you're going to draw a bunch of random numbers, and some of them you're just going to discard. And if you keep track of how many you don't discard, that maybe can give you some interesting information. And so that's sort of what we're doing here with that Monte Carlo sampling, and you'll get a lot of experience with that during the Lab 3 experience. All right, the other thing you're going to do in Lab 3, which is also a Monte Carlo case, is simulate this so-called stochastic activity network, which I've kind of drawn here with these different colored boxes. And so we went over this last time. You can think of this as a breakfast example where you've got some leg of the breakfast taking 3 steps, the other one taking 2 steps, and the other one taking 1 step, or any other process where 3 things can happen in parallel, but they have multiple steps. And so each one of these 3 steps takes no shorter than 2 minutes, but no longer than 4 minutes, and is uniformly distributed between 2 and 4, and the same for this one and this one. So the average time for this is 3 minutes, the average time of this is 3 minutes, and the average time of this is 3 minutes. So the average length of this going from start to A to B and to finish is 9 minutes. Similarly, the start to C and C to finish, each one of those takes no shorter than 3 minutes, no longer than 6 minutes, and an average of 4.5 minutes, and is uniformly distributed between 3 and 6. So these 2 times get added together, and the average 4.5 plus the average 4.5 gives an average 9 for this middle path. And this one, which is just a single activity, there's no addition here. This is just, it takes no longer than 6, or no shorter than 6, no longer than 12. The average here is 9 minutes. So the bottom one takes an average of 9 minutes. So all 3 paths take an average of 9 minutes. This activity is only complete when all 3 paths are complete. So the so-called critical path is the path on any individual realization that takes the longest amount of time. So you could draw 6 random numbers, add these 3 together, add these 2 together, and then just leave this one as it is, and then ask, is this sum larger than this sum? And if it is, then is it also larger than this one? Whichever one is bigger, this sum of 3, this sum of 2, or this single one, whichever one is the biggest is the one that corresponds to the critical path. And so the interesting thing is what's the distribution of critical path durations, or sorry, what is the distribution of durations of the whole thing, which is the same thing as saying what's the duration of the critical path duration. So what's the duration of the longest duration? Then the other thing you could say is what is the discrete distribution of how often each path is the critical path? So how often is path 1 the critical path? How often is path 2 the critical path? And how often is path 3 the critical path? And then it's sort of, I'm kind of giving a little bit away here, but you'll find out that if you did this right, that these 3 paths, it turns out that one of these paths tends to take a little longer than the other paths, even though the average time it should be the same on all three of these. So you can have the average times being the same, and yet the duration of the whole thing being mainly driven by one of these. So one of these, even though it's average, even though all three averages are 9 minutes, one of them is going to be sort of, you can think of one path as going to sit right at 9 minutes, and then another path is going to be a little fatter. It might, have a curve that is going to be less compressed around 9 minutes, and the other one is going to be pretty fat. And the one that's pretty fat, even though it's centered around 9 minutes, is going to be more likely to have times that are much larger than 9 minutes, and that's what's going to cause it to be the critical path more often. All right, so this notation, UAB, as I hinted before, this is a random variable that's uniformly distributed from A to B. It takes any value between A and B, sort of, I use this term equally likely, but what that really means is sort of any small interval between A and B. It doesn't matter sort of where it is, but it has equal probability. And the critical path is the path with the longest duration for a single simulation run, or we might say a realization. So how do you do that in Excel? If you wanted to draw a random number between 0 and 1, then you just use rand. So equals in the cell, rand, open parentheses, close parentheses, and that will give you a single realization of a random number between 0 and 1. If you then wanted to generate a random variant that is uniformly distributed between A and B, then you can use that with a little bit of scaling. So we say, well, how long is the interval? So you just end up saying B minus A, that gives you the length. And then you shift it up by the lower part here. So if this was U56, then this would be rand times 6 minus 5 plus 5. And that 6 minus 5, of course, would just be a 1, so effectively just be rand plus 5. And so that should sort of make sense, that if this generates a random number between 0 and 1, and you did rand plus 5, then this would generate a random number between 5 and 6. So this is the formula you need to use in order to implement each one of these. All right. So before we move on, again, this is going to be a short lecture, but I do want to stop and ask a few comprehension questions. So let's head back to Canvas and take a look.